All right. So, where were we? We're here. Okay.
I'm going be
Can we see
online,
the screen,
sir.
please?
No, sir.
Ah, we can't see the screen. Can we see the screen? Benny, please mute your mic.
Yes, sir.
Okay. Okay. We can see the screen, right?
Yes, sir.
Oh, thank you so much.
No, sir.
Ah, who is saying no? Everybody, every other person can see the screen, right?
Yes, sir.
Yes,
Okay.
sir.
Okay. Okay. Thank you. All right. So let's move quickly. So I've mentioned that J.D. Thompson here. We've talked about that discovery of electron. The credit is given to J.D. Thompson, while the structure of the atom and the discovery of proton, the credit is given to Ernest Rutherford. So you must be able to compare what are the differences between J.D. Thompson model and Ernest Rutherford model. Okay, so you must be able to know what is the modification Rutherford did that kind of make a significant difference from J.D. Thompson's model. So to see what J.D. Thompson worked on, we can have a picture online here. I see here now. So this is the discharge tube or the cathode ray tube that he used. Kind of a more picture here. Uh, can you see this web page?
Yes, sir.
Okay, let me
No,
admit
sir.
the person that wants to.
Yes.
Okay. So he said that, as you can see here now, if you want to describe this, let's say this image for example, this is a sphere, and within this sphere you have positively charged particles and negatively charged particles. But you can say that the negatively charged particles are enclosed. They are enclosed within small spheres. These are small spheres, like a small enclosure. So the whole of these bigger sphere are positively charged, but within these small spaces are negatively charged particles. Why for? So do not forget, he used the cathode ray tube. Let's see, Ernest Rutherford atomic model. So Rutherford atomic model, yes. Whenever you search that, you see he was the one who gave us the structure of the atom. So you can see this is the structure of the atom which we've talked about. So do not forget, we mentioned that there is this positive center where you have the nucleus, and within the nucleus is the proton. So revolving around this positively charged center is the electron, which are located in orbit or shell. But he didn't mention that electrons position on the shell are fixed. So he kind of thought that these electrons can transit, or they can, like, he kind of thought that they are not that fixed in the shell that they have. So that was the modification that Neubauer did. Do you understand? That was the modification that Neubauer did. So Neubauer just kind of stated that the Bohr redefined Rutherford's model by proposing that electrons move in fixed energy level, emphasis on the fixed energy level or shell around the nucleus. So electrons can jump between shells by absorbing or releasing energy. This one we will talk more about that when we get to a particular aspect in physics, maybe, but cannot exist between shells. So this model is still widely used in introductory chemistry to today. Okay, so let's just move from here. So on this page, we're going to be looking at subatomic particles. Yes. So the atom's architecture, it consists of two main regions. You have the nucleus. The nucleus is occupied at the center, and the electron shell surrounding it. So this nucleus is dense and contains protons and neutrons tightly packed together. Oh yes, we didn't include who discovered neutrons. So please note, that was James Chadwick. We'll be given assignment to check up some of these discoveries, and likely we're going to have more discussions on that, or maybe questions and answers session on that by next class. So these are the subatomic particles. As you can see here on this table, you have the particle, you have symbol, you have charge, you have their relative mass, and you have their locations. Okay, so yeah, sorry. Okay. So you have photon. Photon, the symbol is, as you can see, P plus, and the charge plus 1. Plus 1. Relative mass. That will be relative mass to. Okay, relative mass is just like, let's say, mass of the photon itself to mass of another photon. Let's put it that way. Yes. So that's 1. Location inside nucleus. We can see this whiteboard, right?
Yes, sir.
Yes, sir. Yes, sir.
Mass of photon 1.6 sorry, times 10 raised to power. Who can remind me that mass self? Anybody? Am I right with that? So mass of neutron is same thing as mass of photon. So 1.6 times 10 raised to power 10 raised to the power of negative 24. But mass of electron is kind of different from that. Mass of electron is 9.1 times 10 raised to the power of negative 31 kilogram. So when we are talking about relative mass of photon, relative mass of photon would be the mass of photon over mass of photon. Or let me just say that on that table that we're discussing now, or that we saw on that slide, relative mass, what the relative mass is all about is just mass of the particular particle to the mass of photon. Do you understand? So when I'm talking about a particular particle, let's say photon for example, if I want to calculate the relative mass for photon, it will be mass of photon itself divided by mass of the same photon. If it is relative mass, let's say for neutron for example, now it is for neutron, that will be mass of neutron divided by mass of photon. But just because they have the same mass, it gives 1.0. 1.0. But if we are to do that for electron, if we are to do relative mass for electron, you're not going to be having 1.0. Rather, you are going to have a ratio, which the ratio conforms to be 1 over. Okay, let me write that in detail. Sorry. Okay. So relative mass of photon, I mean mass of electron over mass of photon. So this will give exactly this ratio, 1 over 1840. So that is what you have on that slide. Okay, so I hope you are not confused. And the location, Location of proton, you have that inside the nucleus. Neutron, you have that inside the nucleus as well, and electron, you have that inside the within the shells. So as you can see here, protons and electrons are collectively called nucleons. Yes, this is an important word, an important name that you need to know. Nucleons, Nucleons. That's a combination of neutron and proton. We need to take note of that. That proton plus neutron is equals to nucleon. They are found within the shell, or within the positive center rather. Okay, so you have this one there, you have this one there. If this is the proton and if this is the neutron, so the two of them combined together, that's the nucleon. Okay, okay, let's move. So atomic number, yes, need to know the atomic number. Atomic number is usually denoted by letter Z. So, and it is the number of protons in the nucleus of an atom. It is the number of protons in the nucleus of an atom. So, which means that for hydrogen as an example, hydrogen is having just one proton. So since the proton number is 1, you expect the atomic number to also be 1 as well. Oxygen. Can we still hear me?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Hydrogen. Let's say letter H for example. You have the atomic number usually written just beside it here, kind of towards that side. So this small number is the atomic number. This same hydrogen here is going to have another number at the top, which is something we call the superscript. This one, subscript. This is a subscript, while the one up here is superscript. So this superscript is what we call the what? Mass number. So which means whenever you have an element denoted, let's say X, atomic number will be here and the mass number will be up there. So with that representation, I'm using A to denote the mass number, Z to denote atomic number. If I don't want to call it atomic number, I will call it what? The proton number. And you not forget that this mass number, you need to know, is the addition of proton and neutron. So the X there is what? The element symbol. Are we together?
Yes, sir.
Okay, thank you so much. So oxygen as an example, or oxygen for example, O8. So you expect the atomic number of oxygen to be what? To be 8, right?
Yes, sir.
Okay, thank you. Alright, so I think we are kind of done with that explanation of atomic number, mass number, and the likes. Okay, so you have that. So number of protons equals number of electrons. So please know that. But yes, number of protons will be equals to number of electrons. That is for a positive, for a neutral atom. As long as the atom is neutral, the proton number will be equals to the electron number. Who can tell me why? What do I mean by as long as it is a neutral atom? That the proton number will be equals to the electron number. Anybody? Can we hear me? Are we still connected? Are we still connected?
Yes, sir.
What do I mean by for a neutral atom? As long as it is a neutral atom, the proton number will be equals to the electron number. Why did I say that? The reason is because if the atom has probably lost an electron or gained an electron to become an anion, anion is an atom that possesses a charge. So let's take for example, this is oxygen 8. At times you can see oxygen like this, O2 minus. That 2 minus there indicates a gain of 2 electrons. Now electron number here for this oxygen 8 is now okay, let me do this way, is now 8 plus 2, which is equals to 10, but the proton number still remains 8. You can see that they are not exactly same. 8 is not same thing as 10. Reason being that this element here, or this atom here, is no longer in its neutral state. So because it's no longer in the neutral state, you can't say that proton number is equals to the electron number. No. The case is different if it is just oxygen 8 where you don't have any charges there. So here electron number is exactly 8, proton number is also exactly 8, so they are equal. They are equal here. Alright, so I hope we understand that.
Yes, sir.
Okay, let's continue.
Yes,
So
sir.
with this, how we calculate for mass number, you simply just sum up proton number and the neutron number, so you have that. So known elements 118, natural elements that we have occurring, that's 92, and then electron mass, these are just like a quick they are just things to capture your eye actually. So isotopes is also one of the things that negates the Dalton's atomic theory. Remember in the statement that I said, atoms of the same elements are alike in every aspect. This statement here, where is that statement? This one. This number 3. They are not exactly alike. Atoms of the same elements are alike in every aspect, but differ from that of all other elements. They are not exactly alike, even though they are of the same element. So the existence So the existence of isotopy negates this statement, which, for example, what do you mean by isotopy? It's actually a phenomenon where atoms of the same element have same atomic number but different mass number. Take for example, do you get that definition for isotopy? Chlorine 17, 17.
Yes, sir.
Okay. This one 35, this one 37. Okay, of course, it's for the same element, chlorine, yes. But the atomic number here is 17, 17. And actually, the mass number differs, 35 and 37. Same for oxygen as well. Oxygen will have oxygen, yes, atomic number same, 88. But the mass number, you could have oxygen 16, oxygen 17, and oxygen 18. This implies that because of these differences that you have here, they must have a difference in what? Okay, you remember that mass number is the summation of proton number and what? And neutron number. So suppose that proton number is fixed. This one is fixed because it is exactly same as what? As the atomic number, which is exactly same as atomic number. So atomic number is fixed. So the thing that is causing this difference in isotopy is what? Neutron. So I'll call this one the culprit of we call it the culprit of mass number what? Mass number derivation. So it is the one that is causing that change, or that difference is rather. So yes, it's not okay. Before moving there, so all these elements that I've mentioned here, all these atoms rather that I put here, these are referred to as what? Isotopes. So isotopes are elements that exhibit isotopy. But isotopy is the phenomenon where atoms of the same element have same mass, same atomic number, but different mass number. So isotopes are the elements. So that so let's get back to the slideshow. Okay, so these are examples of isotopes here on this slide. Okay, we okay, let's go through. Isotopes are elements of the are atoms rather of the same element that have the same atomic number but different mass number. Yes, because they have the same number of protons. Isotopes of an element share identical chemical properties, but their physical properties such as mass and stability may differ. So yes, their chemical property is same. Whether oxygen 16, oxygen 17, oxygen 18, they still possess the same chemical property. You'll be able to support combustion, you'll be able to combine with metals to form oxides, all of that. So it doesn't make it to change, but the physical property may differ. Do you understand? So these are some more examples of isotopes. You have hydrogen. Yes, hydrogen occurs in 3 possible states. Protium, that's hydrogen 1. Deuterium, that is hydrogen 2. And tritium, that is hydrogen 3. These are all isotopes of hydrogen. Okay. So chlorine as well, you have chlorine has 2 major isotopes, chlorine 35, chlorine 37. So with their relative abundances there. When we are talking about relative abundances, it's just the percentage of of occurrence of elements, of atoms of an element in nature. I'll go over that again. Relative abundance is just the percentage of occurrence of the atom of an element in nature. So here, the relative abundance of chlorine 37, that's 25%, and the relative abundance of chlorine 35 is 75%. Okay, and these are some of the areas of applications of isotopes in medical diagnosis, scientific research, cancer treatments, industrial uses, and all of that. So, electron arrangements and electron configuration. So all these atoms we'll be talking about all this while, electrons are arranged into their shells. For example, let's say oxygen 8, for example. This oxygen 8 we are talking about, of course, the proton number is 8, which implies that the electron number is also 8. But how do we write out the what's it called? The electron configuration? So first thing first is that you need to understand what are the kinds of electronic shells that we have. What are the kinds of electronic shells that we have? Could have a diagram like this, for example. Okay, let me just use that. It's meant to be more circular, but let's manage it that way. Okay, let's consider this to be atomic structure. So each of these circular structure are representing the shell. So you have the K shell. It actually starts from K. K, L, M, N, and it continues. You can have O, you can have P, continues like that. Now, okay, for this shell that you have here, K, L, M, N, they have maximum number of electrons that they can accommodate. Maximum number of electrons that they can accommodate. And for this shell, please, you need to know that it has a certain integer number. Sorry. Okay. It has a certain integer number, which is something we are actually going to call principal quantum number. Formula for this one, 2n squared. So for this one, sorry, for K shell, n is equals to 1. For L shell, n equals to 2. For M, n equals to 3. And for this one, n equals to 4. So what do I mean by n? N equals a principal quantum number. And what does it denote? This letter small n that you have here, what it denotes is that it denotes the distance of the shell. Oh, sorry. Distance of a shell from the nucleus. Okay, that is what it not. So because the nucleus is right here in this center, so distance from here to here is said to be 1. Distance from here to here is said to be like 2, like that. Are we still together?
Yes, sir.
Okay. So when you do 2x, when you do 2x, okay, when you do 2x squared for this one, you have that to be equals to 2 for this. When you do 2n squared for this, that is 2 into bracket 2 square. You have this to be 2 multiplied with 4, which is 8. When you do 2 into 3 square here, you have this to be 2 multiplied with 9, which is 18. And when you do 2 into 4 square here, you have that to be 2 times 16, which is 32. So this implies that your K shell can accommodate a total of, or a maximum of 2 electrons, L a maximum of 8 electrons, M maximum of 18 electrons, N maximum of 32 electrons. So that is what we'll be trying to say on this slide. So whenever we now have something like that, when we already explained that, how do we now write the electron configuration? So it goes with the fact that you start first with your K shell. You start first with your K shell. So let's say, for example, remember you've highlighted that K shell can take a maximum of 2, L shell can take a maximum of 8, M shell can take a maximum of 18, N shell can take a maximum of 32. So we now want to write the electron configuration. Let's take, for example, for hydrogen. Hydrogen, for example, that's hydrogen 1. Electron configuration is just 1, because that's the maximum number of electrons this one has. It's just 1. Now for oxygen, for example, oxygen is 8. Okay, please note that this one that you've written here is only in the K shell. Okay. Now for oxygen, which is 8, your K shell, yes, is going to take the full number, which is 2. Take the full number, which is 2. You're going to have 2, and then you're going to have 6. Your L is here, so which means L for hydrogen is 0. L for oxygen is what? 6. The K shell is 2, so 2 6. And then for phosphorus, which is 15, you have that to be 2, 8, and then you have 5. That means that is having M. So that has M now. Do we understand?
Yes, sir.
Okay. Then can someone tell me for calcium how is it going to look like? Can someone tell me for calcium how is the electron configuration going to look like? How many in K shell?
2 8 7.
2 8 2 8 what?
7.
7. Did you check the atomic number? Remember, you're going to use the atomic number as a guide. That is what you want to do. Atomic number as a guide, provided it is a neutral atom.
2.
You said what? 2?
2 8
8. Yes.
2882.
That is
Yeah.
2882.
Okay, 2882. Thank you. So 2882. That is KLM. This is all still part of. Okay, let me see. This is K shell. This is the L shell. These two here are still within the M shell, okay? Because maximum of M is 18, but you have 10 there, so that's for that. Now, suppose you want to write for this one. Electrical configuration for Hashim 2 plus. Can someone help me with this? How will it be? Anybody?
2,
Okay, 2.
8,
Okay,
8, 8.
okay.
That's all.
That's all right.
Yes, sir.
Okay, very good. So because it has given out 2 electrons, it has given these 2 electrons that you have here. So that's why the 2 is no longer there. So which is why I mentioned that for this kind of atom, now this is not a neutral atom because it is possessing a charge 2 plus. So having a charge of 2 plus means electron number is now 18. But for electron configuration, what we are particular about is the electron number. Please don't just be so focused on the mass number, atomic number rather. So anyways, let's move away from that. So that is electron configuration. So applications and class summary. So you want applications there: medicine, nuclear energy, electronics, and electronics, chemical industries, environmental science, and in agriculture. So that will be the end of the lecture. So I will send this file to the platform there, so you can go through that. So for assignment, will be communicated on the group. Okay. Can we still hear me? Are we still connected?
Yes, sir.
Okay. So
Yes,
so that will be the end of the session. So we can leave the session. Assignment to be communicated on the group, so you should check that. For tomorrow, it will be physics.
okay, sir. Thank
All
you,
right.
sir.
You're welcome.
Okay, sir.
Bye bye. You're welcome.
thank you, sir.
Mhm.
You're welcome. Bye bye.